Good afternoon, everybody. Today I will present the features and design specifications of Gyrofuse, a multi-material anterior lumbar interbody fusion cage designed for reduced vertebral subsidence. The system relies on a two-part hybrid design, an inner additive manufactured titanium core and an outer bioactive composite sleeve. Now, for the first component of our implant, we have a medical grade 23 titanium core. This titanium core has an overall footprint dimensions of 40 millimeters in width by 30 millimeters in length. Now, to accommodate for sagittal alignment in the vertebrae, the component has a 4.5 lordotic angle, which makes the anterior height 9 millimeters and it reduces down to 4.53 millimeters in the posterior face. The exterior corners in the front have a fillet of 6 millimeters, while the exterior corners of the back have a fillet of 4 millimeters to prevent any stress concentrations in the corners of the implant. Now, this titanium core is divided in two regions. The first region is the anterior face, which consists of a 28.2 millimeter solid block. In this solid block, we have 3 screw holes that features a 3.41 radius entry, followed by a 3.25 millimeter guide for standard A-lift fixation screws. Now, on the second part of our component, we have the posterior side, which introduces a 60% porous gyroid lattice structured with 7 millimeter unit cells. This lattice propagates all along our end plate, our titanium core, which helps reduce overall stiffness while improving load distribution from one end plate to the other. Now, the second component of the implant is a composite sleeve manufactured from nanohydroxyapatite and polyamide 66. For this video, a prototype made from carbon fiber reinforced PLA is used to demonstrate instead. When joined with the core, the sleeve expands to a full device footprint of 42 millimeters in width by 31 millimeters in length, maintaining the same 4.5 lordotic slope. And then the anterior height is 13 millimeters in height by 8.71 millimeters in the posterior height. Now, there's a few key geometrical elements on the sleeve design, including a bone graft window of 28.92 millimeters by 12 millimeters. This bone graft window allows surgeons to place osteoconductive bone graft material to promote bone ingrowth in the titanium core. There's also the outer edges, which have the same 6 millimeter fillet on the two corners in the front and the 4 millimeter fillets on the two corners in the back, with a 0.5 millimeter applied in all edges of the sleeve. Now, there's 3 anterior openings, 2 on the top and 1 on the bottom. These are designed to further guide the screw into the vertebrae, allowing the screws to hold onto the vertebrae and pull the implant into the vertebrae, fixing it together. Now, the core and the sleeve are assembled through a mechanical interlocking mechanism. The hollow interior cavity of the polymer sleeve tapers from 39.66 millimeters by 9.2 millimeters in height, and then in the posterior inner wall, it is 36.5 millimeters in width by 4.62 millimeters in height. Using the chamfers in the titanium core, it is guided into the sleeve, allowing a smooth transition of both materials together. Now, once the titanium core is inserted, there's a small protrusion in the sleeve of 4.32 millimeters with a height of 0.62 millimeters in the inner floor of the sleeve. This corresponds with the opening on the bottom of the titanium core, and it creates a snap fit interface which prevents any axial displacement of the two components once they lock together. This helps the components stick flush in the anterior face and allowing the surgeons to now have to worry about the components moving before inserting the implant in the patient and introducing the screws.